Hey, Physics 12. I just wanted to go over a couple questions that might throw you a little in the package. All right, here we go. First guy, you got this cathode ray tube question. I'm not going to throw anything like that at you on any test or anything. These used to be super important because they were all computer monitors and TVs, but they've become significantly less important with LCD monitors and TVs and all that. Anyway, I'll go over it briefly just so it's not confusing. Cathode ray tubes fire electrons between plates, sometimes magnetic fields too, but in this case it's just plates. And between the plates there's electric fields. And the J plate can, normally the electron will just hit the center of the screen and make it light up in the center of the screen. But depending on the voltage of these guys, it'll deflect up or down, and depending on the voltage at plates K, it'll deflect side to side. Now it says there's a potential difference only applied to the set of plates at plate J, so up-down plates. So it can't be A because it's deflected side by side. That would be only K. B says neither of them, like there's no deflection, so neither plates would be active. D would mean both are active, so it's got to be C. Next guy I want to go over is this sucker. It's a little deceptively difficult, even though the answer is quite simple. The how you get there is a little funny. So we got these two equal positive point charges, and first they're a distance r apart, and then they're a distance 2r apart. And you want to figure out how their electric field changes and how their electric potential changes as they move further apart. Now, the trick with the electric field, which is probably the harder thing, thing that might trip you up a bit more, is this is a symmetrical situation. Electric field is kind of like net force per charge. But if you had a positive particle at point P, if they're both closer together and they're equal and opposite, equal distances, they're going to be pushing, this guy will try and push a positive charge at point P to the left with some electric field. This guy will try and push a positive charge at point P to the right, and it'll cancel. So it's zero in this case because it's symmetrical, equal charges, equal distances, pushing in opposite directions. And it's equal and opposite if you move them a bit further apart, but it still stays symmetrical. You got equal charges and equal distance pushing in opposite directions. So two forces cancel, two effects cancel. So your new electric field is same as the original electric field at zero. The new electric potential, your formula is KQ over R. With these guys, it's a scalar, so they're not canceling, they are adding. But in this case, if you move them twice as far apart, because it's KQ over R and they're twice as far apart, you get this extra 2 below, you end up with half the voltage at point P, if they're twice as far apart, just with the formula. And the fact that they don't cancel because it is a scalar, not a vector. It's got units involving joules, not newtons. Next guy I want to go over is this sucker. This one is tricky not because each step is hard, but because there's a fair number of steps. So first we got an alpha particle, which hopefully you're familiar with from the SNAP questions, 2 protons, 2 neutrons. So we're going to have to use information in the table of values, your formula sheet. So our first, why don't we start at the beginning? So originally our goal, our final goal is to figure out the acceleration, which we're going to use F net equals m times a. So starting at our last goal, our only acceleration thing that we know is F net divided by m. That will apply in this case. But to find F net, we're going to need to find the electric field. So easiest way to find the to find the force is the electric field strength times the charge. But to find the electric field strength, we got to use our whole plate equation here. So we got to find the voltage difference between the two plates and divide by their separation distance. This thing doesn't matter. We only care how far apart they are, not how long the plates are, or how wide, or whatever. So that's how we're going to do it. And again, easiest way to solve these things is often to work backwards. Like, hey, I want the acceleration, but to find the acceleration, I need to find the force. But to find the force, I need the electric field strength. But to find the field strength, I'm going to use this formula and then propagate through. So starting at the beginning, we find the electric field strength using our voltage difference divided by the distance between them. We get our electric field strength, which I believe is 2,000. Our charge is, it's an alpha particle, so 2 protons, 2 neutrons. Neutrons have no charge. Protons have a charge of 1.6 times 10 to the negative 19, the elementary charge. So we do our electric field strength times the charge of the alpha particle, which is 2 protons, at least the charged part. And then our acceleration is just F net divided by m. So we get our net force divided by our mass, which is a little tricky. I just use the mass of a proton times 4 because the mass of a proton is effectively the same as the mass of a neutron, a difference of 1.67 and 1.68. Alternatively, you could say 2 times 1.67 times 10 to the negative 27 plus 2 times 1.68 times 10 to the negative 27. But the difference is very minor and I don't care. And that's it. That's how you solve that guy. If you got a proton traveling at the same velocity as the helium nucleus and then sent through, why would the acceleration of the proton be larger than the helium nucleus? Basically, it's exactly the same process. The electric field will be exactly the same, but the force will be 1/2 because it's half the charge, but it's a quarter the mass. So if you have twice the force, or sorry, half the force divided by a quarter of the mass, it'll still have twice the acceleration. So that's the gist. Half the force because it's half the charge in the same electric field, and it's a quarter of the mass because it's 1 nucleon rather than 4. And so that's how you do part B. Next question is pretty easy. I'm going to skip a lot of them and just do some harder guys. There we are. You've done these guys. We haven't done a ton of these electric field ones. In this case, it says we're looking for the electric field for 2 opposite unequal point charges. Now, the electric field lines point in the direction a positive charge would be pushed. So they will be pushed away from a positive charge, so this must be positive, and they will be pulled towards a negative charge, so this must be negative. The number of field lines coming out of a point is proportional to its charge. So bigger charges have more field lines. It's just how we represent it. So in this case, notice we got the same number of field lines. It's also, you get symmetric fields if they're the same charge. So we got a nice symmetric field here. So we have equal but opposite charges. Here we have equal identical charges. We got field lines coming in. So definitely they're both negative because positive charges are being attracted to them. And it's nice and symmetrical. And if you counted the lines, you'd count the same number of lines going into them in both cases. So this is 2 identical equal charges. So they're both the same charge and the same polarity, like positive, negative. Here is the answer. We've got 2 opposite charges. We got a positive charge and a negative charge, but we've got this not symmetric field. Notice the negative one is dominating. It's got more field lines going into it than this guy. And this is 2 negative charges, but this guy is stronger than this guy. And that is how you do the field lines. This guy I'm going to skip. All right, we got this guy. He's tricky until you realize that you should probably do a free body diagram for it. It's really useful that this guy is stationary, so all the forces on it have to cancel. And if you break this tension force into two components, a upward component and a leftward component, the upward component fights the only downward component, which is gravity. And we can find gravity pretty easy. It's just mass times 9.8. So if we do that, we get 0.02. So our upward pulling force is 0.02. With a little trig, tangent here, because we got the adjacent side and we want to find the opposite side, we can find Fx. So if we do Fx, we'll put it in our calculator, we get it's 0.005 if we do tan 15 times 0.02. So then we got this guy, but you might ask, why do I want that guy? Why you want it is because it's equal and opposite to the electric force. The electric force is pulling the ball to the right, and the x component of the tension is pulling it to the left. So they're canceling out. It's not moving. It's not accelerating. And so all you have to do to find the charge is, you know, your electric field strength is newtons per coulomb. So it's just force divided by charge, newtons divided by coulombs. If we rearrange that, solve for charge. If we do our force, our 0.005 as an electric force divided by our electric field strength, which they give it to us, we get our charge. And we're done. That's how you do that. All right, this guy is a little funny unless you you use your knowledge of math in physics. So hopefully at some point in math, you would see a straight line like this and you'd be like y equals x, or y equals some constant times x. So that would be that graph. This graph y would be equal to the square root of x. This would be equal to y equals 1 over x, or potentially y equals 1 over x squared. If you think about it, as x approaches 0, 1 divided by 0 approaches infinity, and as x approaches infinity, 1 divided by infinity approaches 0. So you kind of get the gist there. And then you got y equals negative x, or negative ax plus b. So it's just going straight down, kind of. And so those are that. And then you think about your electric potential formula, which is kq over r. So just some constants which don't really affect things divided by r. R is our x value. So this is kind of the same idea with some extra constants as this. So that's usually how I solve questions like this. I recognize the shape of the graph from like my math classes, and then I just ignore all the constants and be like, okay, effectively what formula is this? So I look at my like x-axis and be like, oh, it's r. So I care about r, I don't care about the other guys. That's how I do those guys. All right, for a question like this, anytime it looks for speed, it's going to be a conservation of energy for electrostatics. So initially it's got a certain amount of potential energy, later on it's got this potential energy, and you just got to do a before equals after. So before you have potential energy using kqq over r, which with this separation distance, and then after you got less potential energy because they're further apart and they're repelling. So you'd use kqq over 8 times 10 to the minus 10. And then the difference in energy, the potential energy you've lost has all become kinetic. And so you just do that. Plug in the numbers, solve for your velocity, and you are done. This guy trips up a lot of people. This one's a little tricky, just because it's a different form than you usually see questions. The question states that, hey, at this point P, the total electric field, because of these two charges, is 8,500 newtons per coulomb to the right. But it doesn't tell you what Q2 is at all. So really our strategy will be to figure out, hey, what is this trying to make the electric field at this point at? And then this guy's got to account for the difference. So the difference between the electric field that this would cause and the total electric field of 8,500 is going to be equal to the electric field due to this guy. From the direction of it, we can figure out the polarity of this charge, and then we can just do EQ equals KQ over R squared, with EQ being the difference between the total and this guy's cause. And we can use that to solve for 2. So here we did it. If we solve for what this guy would make the electric field here on its own, it would be pushing a positive charge to the right, and it would have a total value of 5,000. So if we go and plug it all in, 20 microcoulombs times the constant 9 to the 9 divided by 6 squared, we get 5,000, but our total is 8,500 newtons per coulomb to the right. So this guy has got to be making up the difference. The extra 3,500 has to be because of this guy. And since it's also pulling the charge to the right, that means this must be a negative charge. If it was a positive charge, the total would be less than 5,000 because these two would be fighting. But since they're helping each other, this has got to be pulling to the right. And so then we know the electric field because of Q2 is 3,500. It's making up the difference. And we do K, Q2 all over. If the total distance between the two charges is 10 meters and 6 meters between this guy and the point, this has got to be 4 meters. So we do 4 squared and then solve from there. Here's the last one I want to do with you guys. We just got 2 charges, a big positive and a little negative. And we want to know which region, 1, 2, 3, or 4, is there a point where the electric field, because the 2 charges, will cancel and be equal to 0. Now, first I'm going to look at 2 and 3. If you look at 2 and 3, same logic applies to both. If my point is right here, and I have a little positive charge there to figure out the direction, this guy would push a positive charge to the right, and this guy would pull a positive charge to the right. If they're working together, can they cancel? No. So same argument goes for 3, so it can't be 2 or 3 because the 2 are working together. Now, if we put it in region 1, this guy is bigger and closer, so he'll just win all the time. Your formula for electric field is KQ over R squared. If one's closer and bigger, it'll just win all the time. So this guy, the electric field will always be to the left in region 1 because the big guy just wins. But in region 4, the big guy's further away, but it's got a bigger charge. The little guy's closer, but it's got less charge. So there will be a point somewhere in region 4 where the 2 cancel. And that's it. Sorry it's a long one. Thanks for listening. Please like and subscribe.